share it. Thank you. Yeah, I won't forget it. Yeah. All right. So let me double check whether yeah, it's a recording. Okay. So in last Thursday, we talked about the stereolithography based additive manufacturing process. And in the last few slides, we discussed a multi-material additive, stereolithography printing process. So I just wonder if you have some further idea on it, and then we can have more discussion on it, because I think, because I remember last time, it seems, because the time limit, we didn't talk too much about it. So basically, let me give you a quick review, on this multi-material process. So, so for the stereolithography-based approach to realize the multi-material printing, the critical thing is to replace the vat. So as you can see in this illustration figure, there's a vat A and a vat B. So apparently there's some different material in the two different vat. And if you want to print another material other than the one you already printed, you have to first move down the vat and take out the part being printing, and then replace the vat and put the printed part into the second vat and do the printing again. So it's quite complex process, and it has long time to clean and a lot of waste, because you have to clean up the materials, and during the cleaning process there are lots of wasted material. And also it slowed down the process, because you have to switch the vat back and forth, right? So that's why people are thinking about to use this bottom-up building direction, because compared to the top-down, this one's top-down, and this one's bottom-up. As you can see from the bottom-up building direction, there are smaller region of the printing part will be touching the liquid in the vat, right? So that is a good point for replacing the vat during the printing process. And that's why there are some new approach which utilize the this property. And I'm sorry. Basically, there's a PDMS layer is attached to the bottom of the tank, and then the printing will happen above this layer. So that help the separation between the printed part versus the tank. And also, there's a horizontal motion. It moves the platform sideways to break the form of the vacuum. And and also you can see that there are there's another motion will lift up the printing platform, which is this big blue part. And by doing so, another design idea about the multi-SL process is implemented. As you can see, it has multiple tanks. So this one is the resin tank 1, and you have another resin tank, which is here, and there's some red material over here. So basically, the process will go through again go through this print switch process. So first, the part will be printed in this tank 1, and as long as there's some need to print another material, then the printed part will be lifted up and moved to this brush cleaning area, and then the remaining liquid will be cleaned, and then the printed part will be put into this tank 2, such that this a new material could be used to print. And all of this process, you can see, has to deal with the clean and switch process, which cannot be avoided for the SLA-based process. So actually, my question for you guys is, I think we kind of discussed this a little bit. So, and I don't remember who raised the question. Basically, do you guys think what will be the best application for this kind of process? Last time I mentioned some biomedical applications, but as we have other approaches for multi-material, and also they also utilize those polymer-based material. So my question is, do you think this kind of what is the benefit to use this kind of approach? And if there are some alternative, do you think this is still kind of necessary or not? Because actually, I'm looking at the paper in this area. I mean, this multi-material SLA process, and I'm thinking about whether I should go after this direction or not. And I would like to listen to your opinion, and that could be a very interesting discussion. All right, any thoughts on this? Let me. Okay. Any idea? I think one, I will say, critical problem for this is, seems to be, yeah, what Clay is talking about, because the cleaning step between material exactly will be candidate for this. Okay, so you are saying for those same pieces like circuit board would be candidate, but then what's, yes, kind of applications. To Kevin's question, so I'm asking actually both. So, because I mean, without the proper application, you cannot talk about the advantage or disadvantage. So, to me, it's kind of where is the need for this kind of approach, and whether there are some alternatives. Actually, that's my question, because it seems to be quite complicated to realize the multi-printing process. So if we pay that much price for the complexity of the systems, then what we can have, why it's necessary? So that is my question. Yeah. So basically, Clay is suggesting for the same membranes or other thin pieces like circuit board, this kind of method could be a good solution, which I think could be the case, because if you have very thin object to print, that means you don't need to, I mean, although there's still cleaning process. So for those thin pieces, at least you won't have too much. I mean, compared to those block size or those thick objects. It could be, I mean, it's still affordable, could be, for those same material objects. But do you think other method cannot do that? That's my question. I don't remember who mentioned. There's a company called Voxel 8, right? So they are also printing those circuit board or those conductive inks on the using FDM based method. So why that cannot be some alternative, or which is maybe easier or faster? Mm-hmm. Yeah, exactly. Kevin's mentioned that there are some direct writing, the direct ink writing process. Yeah, exactly. So there's a company called what's her name? Optomac, something like that. Yeah, they have direct ink writing technology machine, which is on the market. So you can purchase that, and also they could print some shape. Not only, I mean, they can write the ink not only just on the planar layer, but also they could write it on a curved surface. I saw some example. They are writing ink on a sapphire. So I really think, yeah, that, because I mentioned there's a possible application could be in the biomedical area. But after I checking the literature, it seems to me there's not much actually happened in that area. So that's why I would like to kind of have some more discussion, in-depth discussion on it. Yeah, why this is necessary? It really bothers me. Yeah. So Kevin mentioned, okay, Clay said, struggling to figure out where a cost or time advantage could be seen with this method, but not very creative at this moment. Yeah, I kind of agree. It's also hard for me to figure out that. And Kevin says, so maybe look at applications where the speed of build is desired attribute. Maybe, yeah, but how much it could achieve? That's a very interesting question to answer. This seems to be useful for large. So Tommy's comments. Useful for larger complex planar parts with a limited number of material transition. So you also agree that this is good to print those thin layers instead of object with large height, right? Because I mean, I think that why we have such kind of impression is this cleaning and switch tank processing is kind of a really headache, really complex process, and it makes us to not appreciate this process too much. I would say, and it seems the effort we put on this process is very much, but what we gain is limited. That's my impression on this kind of process. And yeah, but anyway, I will look more in literature. If I find some interesting point, we can well, Clay, basically Clay mentioned, do you know about how large the example part built in the bottom right of slide 46? I'm referring to the red block with assembly. Yeah, I know that one. Very small. You can imagine this size. It's not a large one. Because for for SLA, it's really hard to print large size objects. Remember what I mentioned before, the separation force. So you have always to kind of avoid the attaching between the last layer versus the bottom of the tank. So it just cannot produce too large objects with, I mean, more precise. Wow. More precise, you cannot print object with large cross section. Yeah. What's this? Oh, Kevin's. Oh, one advantage. Okay, let me read this. One advantage of VAT process is that it fast for parts that are less dense. Exactly, like Eiffel Tower took up a big size but not made much of material. Yeah, that is what I mentioned. Small cross section. Yeah. When looking at object technology for photopolymers, these have to be printed in a solid block. And then support material is wasted removed. So if you need a part like the Eiffel Tower, that need multi-material, this method may be desired, but one of the benefits of AM that you can make many design on one machine. So having such a specialized machine go against it. Yeah, I'm kind of agree with you, because basically printing object with large cross section is still the limitation of FDM. So if that is the problems, that means this system also has this limitation. And then that means you cannot print object with very large cross section. Plus, you have very complex cleaning process, right? So basically you have two, I won't say deadly, but very headache problem. So that's why I'm kind of think this work could be a very good exploration of the idea in additive manufacturing, specifically for stereolithography process, but may not be the future direction. I don't know. That's my current thoughts on it. Yeah, and all right, yeah. So actually, the research thread I think is important for SLA is the one Carbon 3D is leading. So that direction I think is very meaningful, because it speeds up the printing process. And for many consumer applications, like the one they are working with Adidas, they're printing the shoes, right? Customized shoes. And that will reduce the process time, the printing time, and the consumer will appreciate it. So, which I think will be a good direction to pursue. But for this multi-material, I mean, at least right now, I don't see much going on later on. All right. So if there's no other comments and thoughts, let's move on. Okay. Then we're gonna talk about some other process. Oh, by the way, I have uploaded a new lecture notes on iLearn. So if you want, you can download it. All right. Let me switch to another. Okay, let me share another one. So then we're going to talk about some other additive manufacturing process, plus some new kind of a development for new process. All right. So the first one is the laser engineered net shaping, right? In short, we call it LENS. So this method is invented at Sandia lab, and basically the part is constructed with metal powder as well, but it's not a powder bed based one. Instead, it is based on the laser the deposition. So high power laser melts the site of deposition, and the powder deposited by a nozzle into the hot spot. And then the laser build up cross sections in raster scan fashion. Table lowered by a layer thickness. So the table will move by one layer thickness. And then a new layer will be constructed on top of the previous one. So this process will be repeated until the building is completed. All right. So, oh yeah, this one. This Optomac is a very famous company in this lens-based method, as well as the direct ink writing-based method. So I would say for this kind of lens process, the biggest advantage of this is instead of building the whole part from nothing, it has the capability to repair the existing part. That's to me, that is very unique compared to other printing process. For others, it's really difficult to print parts, print shape onto existing shape, right? But this one has this capability. And let's check some video in this end. All right. Let me open it. All right. Just wait a minute. I will share the screen to you very soon. All right. So as you can see, for this in this video, some new shape is added onto the basic block, right? And that is, I would say, it brings the new opportunity to additive manufacturing. That is the I would say the most unique feature for this lens-based process. Another point is, Kevin said, okay. Yeah, that is what I'm about to talk about. So Kevin mentioned, I don't have much experience with lens fabrication, but it seems that you might have a hard time making overhangings as well as powder bed. Many of the demo parts I have seen are fairly straight, vertical, like the one in the video. Exactly. Basically, lens also have the problem of the support material. But what I'm about to mention is it has the potential to reduce that. Why? Because I would say the lens process is is quite similar to welding, right? And it could have multi degree freedom. Means you don't necessarily you don't need you are not necessarily sticking to one printing direction, one deposition direction. So if the platform could move with 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 some degree freedoms, then you could deposit from other directions, such that some features, some overhanging features won't be overhangings in certain direction. Do you remember the work I did? Basically, I just introduced one rotational degree freedom and makes the whole part kind of decompose into different pieces. And I just want to find one printing direction such that the print for that direction, the printed part piece has no overhanging features. So similar concept could be applied here because the system already has the potential to have multiple degree freedoms. So that will really change the lens process. Also, for the multi-degree freedoms, it could make this process printing in a curved layer other than planar layer. Because you have these degree freedoms, you could change the printing direction. You could adjust it during the printing process. So that will also bring the new opportunities regarding the overhanging features, the requirement of support material, right? Just imagine if you slice your object not in planar but in those curved layers, there are a lot of features will not be overhanging anymore, right? That's one point. For the curved layer, there could be other benefits. For example, the material properties. Right now, you are not talking about those planar layers. Then the bonding between each layer will be totally different, right? For the curved ones. So actually, that is this lens-based approach. For this kind of approach, I think it has potential by integrating some advanced computational method. This lens plus WAM, this two, I think it has potential because both of the two have the multiple degree freedoms, and it brings the flexibility for the computational method. All right. Okay, let's move on. So another process, we're going to talk the WAM later on, and also a lens a little bit later on. Okay, someone's leaving message. Clay, okay, the curved layer approach. Yeah, it is new. Clay, you are right. So Clay said the curved layer approach sounds interesting. Do you know of any examples? Or is it very new or theoretical? It is very new. I know some brand new work which hasn't been presented. They just publish it. They just expose their publication. but they haven't. It is accepted by a conference in computer science area, but they haven't officially published the paper. But they're still focusing on the algorithm side, and they haven't considered about too much to the about the manufacturing, and they use the fused deposition modeling to demonstrate their algorithm. So I would say it's still under developing, and I'm quite interested in that, in this aspect, and I would like to conduct research on this. So as I think I mentioned to you guys about this research direction. I'm building. Actually, I'm asking my student to build up a testing platform by integrating a pan-tilted table with 3-degree freedom plus a delta printer. So in total, they has 5-degree freedoms, and well, that brings the new degree freedoms. And I would like to kind of prove the concept in using the FDM-based approach. And then, if it works, it can be transferred to metal printing, such as WAM. I'm working with Dr. Kim as well. And if possible, I could find some collaborator who has the lens system. I can also work on that. So that is the current status of the research. Okay, Clem says turning property to control failure methods could be hardy in different applications. So what do you mean turning? What do you mean control failure method? What's that? You mean the control of the printing, or which part you are mentioning? You're specifically mentioning. Different material property result. Yeah. Oh, you mentioned that. Okay. Yeah, exactly. But the thing is, because there's no such process there, so people don't know what's gonna happen. Yeah, definitely there are a lot of unknown problems need to be explored, and yeah, I'm looking forward to that. Yep. Okay, let's move on. So another process is the sheet lamination process. So this kind of process is kind of it has the layer by layer process to laminate the plastic, paper, or metal sheet. So the material, the thin sheet material, will be cut using either laser or some mechanical cutter or other machine tool. And then the different sheet will be bonded between layers by using glue or other adhesive bonding, or some thermal bonding or clamping or some ultrasonic welding. All right. So that's the basic concept for sheet lamination process. And there are different process under this category. So there's laminated object manufacturing, and basically it has different variations in this LOM. You could do the bonding and then do the forming, or you could do the forming first and then do the bonding. Okay, and besides the LOM process, there's also the ultrasonic consolidation. And let's check them one by one. So for the LOS process, the laminated implies laying down of the layers which are adhesively bonded to each other. And it uses layer of the paper or plastic sheets with heat activated glue on one side of the product parts. So basically, the different layers will be bonded by heating up the glue, right? And the excess material to be removed manually. So that is, I would say, a drawback for this. You have to manually remove those extra material. And it is simplified by preparing the laser to burn perforations in cross-section patterns. So the laser will be the method to cut the shape for each layer. And LOM uses sheet as thin as 0.05 millimeter, right? So that's the layer thickness. Sorry. Compressed paper has appearance and strength of soft wood, and often mistaken for elaborate wood carvings. So the paper will be the most widely used material for LOM, but because this process is utilizing paper or plastic, that means the application is limited due to these materials. So here shows a typical systems for a LAM system. And as you can see, so the material sheet will be rolled into this bed. And on top of this bed, there's a laser, right? Laser head, which will cut the desired shape from this whole sheet of material. And then in the other side, there's another mechanism will screw down to pull the excess material. So that is the overview of these systems. And there are some commercial systems like the one over here. So basically, this one is introduced by the Helices company. And basically, it utilizes the paper sheet as a building material. And we can take a look at their process. All right. Okay. I saw some discussion on this. Let me first switch back to the presentation. All right. Oh, great music. Okay. Okay, Doc said is the height exaggerated. What do you mean the height? Which height you're mentioning? Between head and build surface. Oh, that one. So basically, you think the laser will not be too high from the building surface, right? I mean, unfortunately, I never seen a real LAM machine, but I don't know. But what's your concern about this? Isn't there an inverse direct distance to laser power square ratio? So what you are talking about is related to the distance between the, okay, more distance, more power. Oh, okay, I got your point. Yeah, if from that point of view, it could be an issue. But again, you are kind of cutting the paper and the plastic. The power won't, the required power won't be too much. But the thing is, if we take the laser cutter as the reference, yes, the laser head is not too far from the cutting surface. From that point of view, I'm kind of agree with you. Yeah, it could be exaggerated in the video and in the illustration figure. Yeah. Okay, what Kevin said, how would this do with thin fissure? I'm picturing little shaving of paper curling all over the place. Oh, so you mean if only very thin layer, very few layer will be laminated, what's going to happen? Yeah, that's a good question. But actually, I'm thinking there should have some bonding between those layers, and they will stick to each other, and that could help avoid the case you mentioned. If they're bonded to each other and they're bonded to the platform, then even for thin layers, the paper won't curling too much, won't curl too much. That's my thinking on this point. But again, I don't think this could print very thin layers, because after all, the material is not too thin, right? You are talking about some sheet, right? So the printing material determined there won't be too thin features to be printed. So okay, so Kevin said, for Doc's question about laser distance, does finished part come back up to be removed? What do you mean come back up? Oh, to get the finish. Oh, okay. Well, I think that won't be problems, because I mean, it doesn't matter how near or how far the laser head is, because you can always move it. Just think about the laser cutter, right? So it has a kind of XY table, right? It can move in the plane, XY plane. So once you finish the printing, this head could move to somewhere else, and then you can take out the whole thing, right? I don't think that will be the concern for regarding the laser distance. Yeah. Okay. Actually, I have another method. I mean, another company actually, which is called the solid dimension. So instead of paper sheet, they use the PVC plastic sheet, and they use the mechanical cutter instead of the laser cutting. Okay, let's check this one a little bit. I mean, to be honest, this LOM process is also new. I mean, I won't say new. I know the concept, but I haven't personally worked with this system before. So yeah, and that's why it's good to have discussion with you guys, and then we could figure out some problems and insight on this process. Okay, let me share the screen.
Solidu presents its 3D desktop printer. Introducing the SD300, the world's first 3D desktop printer. With its compact size and unprecedented cost-effectiveness, this breakthrough product is making 3D printing available to any office. From concept modeling to final product. Save time and money with the SD300. Now go from concept to final product without using a service bureau, thus reducing costs and time to market. The SD300, revolutionizing the way designers and engineers approach 3D modeling. Plug-and-play desktop installation. With the SD300, operation is made simple using the user-friendly instruction manual provided with the material kit. Install in a matter of minutes. First, insert the engineered plastic roll into the printer. The engineered plastic roll used in the SD300 is both durable and economical, giving you attractive build cost per model. Second, insert the glue cartridge. Third, insert the anti-glue cassette. Finally, place the 3 anti-glue pens. Now just hit the build button on the provided SD View software and your printer is off. Finally, a 3D printer you can afford. The model is created by layers of engineered plastic. Following sheet lamination, the cutting knife goes to work directly from your CAD data. The engineered plastic roll is layered using special glue, resulting in strong yet flexible models. The anti-glue pens then apply masking fluid for easy support removal, allowing even the smallest details to be created. Reducing development costs and time to market. Models are designed down to the smallest detail, and the engineered plastic roll is available in transparent or opaque colors. You now have your finished model in hand, ready for evaluation, without ever leaving the office. Multiple applications. The models produced by the SD300 are so detailed and accurate that they are perfectly suitable for all stages of production, including rapid manufacturing. They can be machined, drilled, finished, joined together, and painted. Larger models can be created as well, assembling one model or multiple models to each other. And all of this while showing no distortion over time. Now Solidu invites you to add another dimension to your printing and change the way you design forever. with the SD300.
Okay. So, okay, let me. Okay, any thoughts on this? Oh, wait a minute. My computer is playing some other video. Okay. Oh, apparently they have some. You guys have some discussion. Okay. Doc said, looks like transparency film from 1890s that always used to melt together. Your presentation slides exactly. Yeah. Yeah. Look good for flatter, shorter parts, but wasteful for tougher parts. Exactly, Kevin. Dog. He put a lot of layers. Yeah, basically they just fast forward. So you never see how much effort they paid to remove all the wasted material and how long it takes. I think I saw a knife at the end of it. Yeah, Robert, you're right. Probably it requires some tool because it seems not easy to remove by bare hand. I would hate to remove material on something like Eiffel Tower. Ours with tweezers and magnifying glasses. Yeah, Michael, I agree. Robert, you also have to have open surface to remove the material, no hollow part. Yeah, if exactly, if there's some internal tunnel, how to remove that? Because basically the whole part is buried in the material. Yeah, you're right. You then the design has the restriction. You either need either need to design some assembly, or you have to leave some features to remove the material. That's the limitation. And okay, I have other thoughts on this. So basically, they are using they mentioned in the video, they are using a knife, a blade, to cut the material. So what's the consideration to use a knife, but not a laser? What could be the main cost? Yeah, that could be one. Thermal effects. Yeah, if the laser to melt to cut the part, I would say it's I mean to cut the plastic, that it's hard to control the heat distribution there. Yeah. Any other thoughts? Okay, Kevin said laser could damage the glue below. Yeah, exactly, and make surface appearance degrade. Exactly. So it really depends on how good you control the laser power, such that it can do the work and not damage the existing one. But similar problem could happen to the paper one, right? How they handle this for the paper? Paper, I mean the previous the Halley system one, right? It used paper and laser cutting, right? I'm pretty optimistic on laser these days after having my okay, yeah, you're right. You're right. Can wavelengths be selected to only affect paper? This, but I think for even for plastic, yeah, even for plastic, I think it's using laser shouldn't be problems. Although I didn't cut those plastic sheet, but I do cut some thicker plastic part. Yeah, probably you need to control the power carefully. Yeah, that must be some something you need to play with the power setting. Exactly what Michael suggested. Power setting and what kind of laser you are talking about. Yeah, if there's they are high power ones or low power ones, or I don't know. Yeah, yeah, that could be the case. Fiber or carbon nitride ones. Yeah. All right. Actually, there are also one source which is different from you guys' comments. That is basically my point is from the marketing perspective. Basically, in the video, you can see they're kind of have the selling point. It is a desktop laser, a desktop 3D printer, right? And if you use laser, even very safe level laser, very low power, it will be difficult to promote the product to be a desktop one. That means you are putting this printer on your desk, and it's an office environment, not a protected environment. So if they use laser, that will make things complicated. I mean, even very recently, there is a desktop laser cutter on the market, but still, when you buy it, the manufacturer will ask you to sign some document. Basically, that it asks you if there is some damage or possible hazard. It has nothing to do with them, something like that. So it's still quite sensitive, and I think that is also another concern for them to not use laser, but a more safe one, which is a knife. So that's my perspective, because I had some experience to purchase this desktop laser machine. All right. Okay. So we can have 5 minutes break, and then we come back to discuss. All right. See you guys in 5 minutes. All right. Let's continue. All right. So this is one when people are removing those unnecessary material from the printed part, right? Also, you can see from the video. So the LOM process has some advantages. First, it has little shrinkage and a residual stress, and also the distortion. So the end material is similar to polywood, and which is a kind of eligible to do the common finishing operations. So you can further machine it. The last part can be fabricated rapidly. So basically, you just need to stick or glue the larger sheet together. A variety of build material can be used, including paper, polymer sheets, and metal sheets, right? And another benefit for this is it is not toxic and easy to handle feedstock. So compared to other printing process, the material cost is relatively low. But there are also several disadvantages, right? So for the paper-based part, basically you need to do some coating such that the moisture absorption will not damage the part, right? And you also need to control the part's accuracy in Z dimension. But that is not difficult. That is not easy because the sheet material could have inconsistent thickness, right? So that really depends on how good of the consistent sheet thickness. Also, the mechanical and thermal property of the parts are inhomogeneous because the glue is used to bond different sheets. So that makes the mechanical property and thermal property inhomogeneous. Also, small part feature detail is difficult to maintain due to the manual decoupling process, right? You have to remove the actual part by your hand or some tools. So it's very easy to damage those features. So these are major challenges or advantages for LOM process. So there are some variations to kind of combine the LOM with other color printing process, like the M-core technology. So basically, they produce those true color 3D objects like this. And let's check what they did. There's a video. We can check the video. Okay, let me share it first. All right. So basically, they kind of integrated this LOM process with the kind of color injecting. So during the printing process, they could, at the same time, they could put the color onto certain regions. But still, it's limited by the material they use, right? So you can see the application of this kind of approach is still quite limited. They can only produce object with appearance, right? So maybe they're good for applications in education or other scenario which does not require a good mechanical property and so forth, right? So another category of the lamination-based method is the ultrasonic consolidation. It is commercialized by this Solidica company, right? So this kind of approach is a hybrid sheet lamination process. So it combines the ultrasonic metal welding with CNC machining together. And we can check it by looking at this video. All right, let me share it. So here shows the ultrasonic welding. After welding, there will be a milling process to shape the layer. All right. So as you can see, this is a kind of a combination of additive and subtractive manufacturing together. And if we check more about this ultrasonic metal welding, we could have some. Oh. Okay, wait a minute. Let me share it.
Ultrasonic consolidation produces direct metal parts from CAD data by ultrasonically welding layers of coiled aluminum foil strips to a prepared metal substrate. As the foil strips are placed on the substrate, a tool called the sonotrode uses high-frequency vibratory energy and moderate force to disrupt the interface surfaces, inducing interatomic attraction and metallurgical bonding between the foil and the substrate surfaces. Once ultrasonically welded, the layer is then milled to the cross-sectional shape defined by the CAD data. This process of adding material to a previous layer and then removing the excess continues until the part is complete, Like other rapid prototyping processes, ultrasonic consolidation also allows for the buildup of complex geometries, overhangs, and enclosures within a part. Ultrasonic consolidation can be used to bond a variety of similar and dissimilar metals, as well as certain ceramic metal combinations.
All right. So that's the details for this ultrasonic welding, right? Oh, I saw some. Is a metal sheet loaded manually? That's a good question. Yeah, possibly. I think just for loading other sheet or strip of other process, it could be loaded manually. But what's the problem for loaded manually? What's the point, Kevin? Oh, okay. I I think what the human need to do is just load the end of this sheet or the strip, and then the roller will kind of automatically load the actual ones, the remaining ones. I don't know how much it's gonna looks very slow. Okay, have to clean and deburr the machine surface between every layer. Matt, you're talking about the whole process, not the loading, right? Not the sheet loading. Oh, okay, okay. Yeah. Yeah, that could be the I would say the major I would say the major drawback of this kind of approach is you have to dig out the whole thing from the rest part of the material, and that's really annoying process. But even for this, even for this, although you have the CNC milling to do the work, I would say it still requires fairly a lot. I mean, I would say a lot of efforts, manual efforts, to make it happen, as suggested by Kevin and Matt, right? So it seems was handpicked for size and location. I think definitely they have size and location. Okay, I didn't notice that detail, but could be. Yeah, I think this kind of approach is quite limited because all these handlings and also their capability to produce the parts. As you can see, I mean, almost every example is not so complicated shape compared to those powder bed or even sintering powder bed melting or sintering based. The material, the object they produce is pretty simple, and these are definitely the limitations. And I would say the most critical problem for this is it involves a lot of manual effort. That is kind of go against additive manufacturing, go against the advanced manufacturing, right? It should be more automated process. It shouldn't be something like this. You have to always manually do something, right? Okay. Okay, let's move on. So basically, this ultrasonic consolidation is something like this. You have this rotating sonotrode, and it will weld the strips, the metal strips, onto the substrate. And after the first few layers is generated, Then new strip will be the new strip will be welded onto the existing layers. So these metal foils will be the building material for this welding process. All right. So for this ultrasonic constellation, it has some advantages. It has better surface finish and high precision compared to the LOM process. But the accuracy depends on the milling approach rather than the foil thickness. So it has a milling process to final finish the surface. And due to there's a milling process, there's no stair steps effect. So all those rough feature will be removed, right? And it is capable of creating complex multifunctional 3D parts by introducing the complex internal features and multi-material. They could be integrated with wires, fiber optics, sensors, and instruments. And also, those multi-material can be put together by using different strips with different materials. So these are the concept for putting the multi-materials together. And also there are some disadvantages. So it lacks of an automated support material. That means to generate support material will be really difficult. And also the waste of material will be large compared to other additives. Because when you have when you put layers together, and then you need to perform a milling process. And during the milling, there are a lot of wasted material. But that's the common feature for the hybrid process, means additive plus subtractive manufacturing. So it has pros and cons, right? So after introducing this ultrasonic constellation, we're going to move to the kind of a new chapter about those emerging additive manufacturing process, some new process compared to those kind of relatively old ones. So we talk about different additive manufacturing process, and they are all have different working principles, materials, powers, and they have their own advantage and disadvantages, right? And let's have some summary on it. So the advantage of additive manufacturing, as you can see, it has all these good features, such as complex geometry, no assembly, customization, those kind of personal design fabrication. It makes people design and fabricate without precising those manufacturing systems. You can just access them using the internet and transfer your design to some physical objects, right? And it has the flexibility of multi-material for this kind of like the one shown here, the statue. You can accurately duplicate a physical object by 3D scanning and then 3D printed, right? Also, for those functional structured material, additive manufacturing enable the manufacturing of such kind of material which is impossible for other manufacturing process. Also, it supports the DIY community quite a lot, like the one shown here. So these kids are building their 3D printer by using the open source toolkits, right? I mean 3D printing kits. So all these good features actually will kind of push additive manufacturing towards some new level. And also all these good features popularize additive manufacturing, right? But there are some limitations. First of all, the accuracy of additive manufacturing is still limited. There are two major effects. One is the stepping effect. So basically, if you check the figure shown here, the left bottom corner, right? So basically, for additive manufacturing, you are using this rectangle to approximate this human head shape. So all these hollowed part will be between this rectangle and the contour of the human head will be the distorted area, and this is called the stepping effect. Also, if we come to the physical process of additive manufacturing, and we will know the accuracy of additive manufacturing will also be limited by the particle size or filament size. And that is by nature cannot be avoided due to the way of the process is implemented. All right. Also, the surface finishing compared to other manufacturing process, especially machining, is still quite low. Yeah, right. And sometimes additive manufacturing could be time-consuming, and the cost will be still high. But although we can justify the cost in some of the application, but in general, it's still quite high. Also, the size of additive manufacturing to generate is quite limited. It cannot be too small, and it cannot be too big, right? And you can only print object in certain range of size. Compared to other conventional manufacturing process, the material can be used in additive manufacturing is still limited. And more importantly, what you generated may not be that reliable in terms of the mechanical and thermal properties. For the manufacturing process itself, is also not reliable. Means you will always have failure cases, right? And even you have the same setup. For different times you print the same objects, you could have some failure cases, and these are not solved yet, right? All these limitations will push the development of additive manufacturing. To give you some better understanding, I list out some limitation and show them in some figures. So as you can see, these parts are additive manufactured, and you can see the surface finishing is not that good, right? You can still see the surface roughness. Actually, they are manufactured using different additive manufacturing process, but still they have the same surface finishing problem. And the post-processing could be quite costly, time-consuming, and could be quite annoying to people, right? There are a lot of manual work to do. For for example, for those metal-based printing, you have to kind of take it out from the powder bed. You have to remove the actual powder, and also you need to remove the part from the platform. And all this requires time, money, and people's effort. Another big challenge is this support material, right? So for many printing process, it requires support material. So printing these support material will be time consuming and a waste of material. And sometimes it will damage the surface itself. For the printing time, so if you check this row, you can see how long it takes for printing the same part. So for some of these material printing process like FDM, it takes almost 2 days to print something, to print the object. And the cost is also high, right? So how to reduce them? That's why people are still working on this area to improve the process and their design such that the build time could be reduced dramatically. That's why I appreciate the work of Carbon 3D, because they are working towards reducing time for SLA process. Right? Also, the material, as you can see, most of the material are plastic or polymer. Although there are some metal printing available, but still the types of the metal it can used in additive manufacturing is quite limited compared to other manufacturing process. Then what's the next, right? What's the next step for additive manufacturing? One direction is the hybrid process. And there are different threads, right? One is the multiple additive manufacturing, means combining different additive manufacturing process together into one process. Another direction could be the combination of additive and subtractive, right? So basically, as I mentioned, as I showed in the previous slides, so for this one, basically it combines the laminated objective manufacturing with the color printing. So they could produce those multicolor objects in this way. Or in this case, basically, as I mentioned before, there are two different types of stereolithography process. One utilizes laser beam to cure the material. Another one uses the projected image to cure this image. So one benefit for using laser is because the laser, the size of the laser spot could be controlled precisely. So at the same time, the resolution of the projection-based SLA is limited by the pixel resolution. So if we combine these two together in this way, such that we use the SLA to cure the contour of the shape, which is the most critical for the surface finishing, and then use the projection-based SLA to cure the internal region, the interior region of inside that contour. Then we could kind of utilize both of the benefit of laser-based and projection-based, because the laser-based is usually faster because you just project the whole image instead of scan line by line. right? So it is faster than laser-based. And because we are using laser-based SLA to cure the contour, so we could have better resolution near the contour region. So we're kind of combine the advantage. We kind of take the advantage of both of the two processes. So that's the concept of this method. So any thoughts on this? Any comment on this method? Yeah, Doc, you're right. It's kind of rough cutting and fine tuning, right? You kind of use this projection based to generate the large area, but use the laser to carefully kind of shape the contour part, right? Okay, what Clay said. Thinking from a control perspective, would there be any issue with sections being cured twice? Yeah, that same spot is bite by light and laser. Yeah, that's possible. Definitely that's possible. So how to kind of carefully control the interference region between the projection cured region and the laser cured region will be the main challenge for this process. So what they actually do is basically they have little gap between these two regions, and for this gap they will kind of do a final scan there, and then that ensures there won't be the overcuring, because the overcuring could be a problem to generate the unevenly distributed layer thickness, as well as the material property. Also, it's also also can be tackled by control the laser precisely, because for the projection it is really difficult to make it precise. It really depends on the image, but for the laser you could make it very precise, and that will reduce the overcuring. Okay, so Kevin said, would you get some cosine error that needs to be corrected since the two sources are not collinear, such that the path of a circle project as a oval? So I don't quite get it for the error you are talking about. If you are talking about the projection-based SLA, well, if the light power is good enough, and also the distance is not too far away, then there shouldn't be too much distortion for the projection. That is what I get at. That's why you cannot project too large area again, because you cannot project a large area and that will gives you oh, okay. Oh, I got your point. The center of the two sources are not collinear. Yeah, oh, I got your point. Yeah. That could be overcome by conducting a calibration. So after calibration, this is the error between these differences could be minimized, and that wouldn't be a big problem. But what I'm talking about, the error, what I'm talking about is about the distance. So basically, if you not only distance but also for the projection, you cannot, if you project it to a very large area, and that means the distance between the projector and the surface, projected surface will be longer, and that could bring some distortion, and that is hard to overcome. But for what you suggested, basically the alignment of the two system can be overcome by conducting calibration. Yeah. And okay, what Douglas said. Could this be done bottom up instead of top down? Yeah, I think so. Does coupling them require top down? I mean, even for the laser based, you could make it top down. I mean, bottom up. I'm sorry, right? There's no limitation for that. So I would say it should be fine. But in this particular implementation, the researcher who invented this method, they chose to use the top down. Okay, Robert said, in general, calibration could be difficult and possible would be required to be performed periodically. So for the first part, I understand it, but why you think it's periodically means you have to do it multiple times? Is that what you suggested, Robert? Yes, due to the drift of the laser control. Yeah, that I think that's the concern. Exactly. If you have two different systems, make them together, you always need to do some alignment and adjustment. But I think the concept here is pretty good. Although for the implementation, there could be different issues, but the concept is, okay, laser has the advantage for the precision, right? But the projection based has the advantage of speed. Then combine them together. Let the laser to do where requires precision, and let the projection to generate a large area. And it's kind of utilize both of the advantage of the two process. And I think that should be the direction which, it should be the way we think about of the problems, how to make them better, how to improve it. Although I agree, there are a lot of practical problems in the implementation of the system. But from the concept wise, we should think in this way, how to kind of carefully select the benefit and put them together. All right, any other comments and thoughts? All right, I think I will stop here, and last Tuesday, we're gonna have one more presentation. I'm sorry, one more presentation. Also, for all the groups, you need to submit me your slides by next Thursday, right? And of course, you need to make sure there's no sensitive material which cannot be shared to me. All right, because I need to keep your presentation as a record for my grading, because this is part of the assessment, right? Actually, the one from Drew, who else? Clay. And Michael? Yeah, yeah. The one from them has been sent to me. I've already have that. So there are two groups. I need you to send it to me by next Thursday. All right? Any questions? Okay, got it, Kevin. Okay, any other questions from other people or comments or anything? Okay, if there's no other things, let's meet on Tuesday. All right. Thank you.